Alright, this should be our last video wrapping up chapter 16. This is a continuation of example 16.3 in which we're designing a timber beam. We have chosen a 2x12 for this particular truss. We checked the bending stress, it was good. We checked the deflection, it was good. We checked shear, it was good. The last remaining thing to check with a timber beam is the bearing area here. So at the end of a timber beam, it sits on top of something. And depending on how big this area is, this rectangular area, it will affect the stress. And as we mentioned before, wood is very strong parallel to the grain, but relatively weak perpendicular to the grain. And this stress, this bearing stress of all the weight that this beam's carrying resting on this little area is going to be perpendicular to the grain. So we have to make sure that this area is big enough so that the stress doesn't get too large. By increasing the area, we can spread out the weight and therefore decrease the stress. So we have hem fir, that's the species of wood we're using in this example. And if we look up in Appendix F has properties of different wood species. And something we didn't write down earlier but perhaps should have was the F sub Cp. That is the allowable compressive stress perpendicular to the grain. And FCP for hem fir is 400 psi. So that's not very large, but that's to be expected because wood generally is not very strong perpendicular to the grain. So the amount of force acting at the end of this beam is, in this particular case, equal to the maximum shear. If I were to draw a real quick beam diagram, when we have a simply supported beam with a uniformly distributed load, and we draw a shear diagram for that, the shape of the shear diagram looks something like this. Starts off with maximum amount of shear at one end, and then that decreases steadily until at the other end it's negative shear, has the opposite sense, but also maximum magnitude. So this maximum shear represents the reaction force at the end of the beam. And we already calculated the maximum shear force and found that it was 624 pounds. So we have 624 pounds that needs to be supported by the end of this beam. So we need to make sure that it does not, this load divided by this area does not exceed this allowable stress. So stress is equal to load, which we've used P in the past to represent load. We can use V for the shear divided by area. And the particular stress here is compression perpendicular to the grain. So we can set up an equation for stress, and if we know the area, if we've chosen an area here, we can take that maximum shear force divided by the area to find the stress and make sure it's less than 400. Or if we're trying to design this area, if we're trying to decide how big that area should be, we can just rearrange that formula and say that the required bearing area must be greater than the maximum shear force divided by the perpendicular compressive force, the force perpendicular to the grain. Stress, rather, I'm sorry, that's stress. So the way the problem is set up in the book, it tells us that the bearing length, so the dimension in this direction for our beam is 3 inches. We have a 3-inch bearing area. In the other direction, we selected a 2 by 12, which has a width of 1.5 inches. So that means our area is 3 times 1.5, which would be 4.5 square inches. So since the area has been chosen for us, we're just checking to see, is it adequate? Is that okay? So the stress is going to be equal to the 624 pounds divided by 4.5 square inches. And if we calculate that, it should equal 138.7 psi. So that's the amount of stress that the end of this beam is going to experience in bearing. Is that adequate or not? Is that acceptable? Well, the allowable compressive stress is 400, and the actual bearing stress is only 138.7. So that is obviously less than 400 psi, and therefore it is okay. So we have now checked bending stress, deflection, shear, and the compressive stress perpendicular to the grain. Sorry, that should be a P, CP, and it is good as well. So those 4 things have all been checked. They all turn out to be okay, and so a 2 by 12 is going to be the proper sized joist to specify for this design problem. Okay, I think that wraps up this chapter.